So this presentation is about using the sample mean, x bar n, to estimate the population mean, mu, if we do not know the population standard deviation, sigma. And this kind of assumes that you have already covered the similar discussion when we do know sigma. This one will be easier to understand if you have gone through that one first. So, the true population mean is probably close to the sample mean, but can we figure out this margin of error, this capital E, like we did in the previous lecture, without knowing sigma? This time let's do 99% confidence. So we want to find a margin of error E so that 99% of all possible samples produce a mean, sample mean, that differs from mu by less than E. And we're going to do the cell division example again. And so we want a number E, so 99% of all samples produce, 99% of all the samples produce a sample mean division time for the cells between these two limits. Now, the previous discussion was based on converting between natural and standardized units. If you remember how that went, we knew that the margin of error, E, in standardized STD units was, well, for 95% confidence, it was plus or minus, well, E was equal to 1.96, almost 2 STDs. Okay. And how did that help? Well, if we could say, okay, E is 2 STDs, we just had to decide, so how many minutes was that? And we could work that out, because each standard deviation of x bar was worth sigma over root n minutes. So you could say, okay, if our margin of error is plus or minus 2 STDs, and we know the standard deviation for the sample mean was 20 seconds in the previous lecture, or 1/3 of a minute. So okay, 2 standard deviations times 1/3 of a minute, and there's your margin of error. Right. So but the Z was the 2, and the sigma was, Z was 2 STDs, and the sigma was, the sigma over root n was 1/3 of a minute. All right. Well, but now that we don't know sigma, we seem to be stuck. Because how are we going to, our margin of error was Z times sigma over root n, and we don't know sigma. Okay. But it's okay, because we have a sample, and we can get the sample standard deviation S. Sigma is the population standard deviation. S is the sample standard deviation. And so the idea is, instead of making the Z statistic, we're going to make the T statistic. The T statistic is just exactly the same thing as the Z, but with the S instead of the sigma. And so a person who was working for a beer manufacturing company had signed a non-disclosure agreement not to reveal anything about the process of making the beer. He was doing statistics for quality control, and he came up with this idea, and he felt that for legal reasons he could not publish it under his own name because of the non-disclosure agreement, but he also felt that the company had no right to claim ownership of a piece of mathematics, so he published it under the name A Student. And so this thing was called the student t-distribution. But years later, his name was revealed to be Samuel Gosett. So I've been calling it Gosett's t-distribution. In a lot of books, you'll still see the name student t-distribution. So it's actually, there's a family of distributions depending on the sample size. There's this parameter nu here, Greek letter nu, it's n-1. And depending on that, you have different distribution curves for the t-statistic. And when the sample size is very large, the t-distribution comes to look exactly like the normal distribution. So this black curve here, the tallest one here, is the normal, standard normal distribution. And these others are standard t-distributions for samples of various sizes. And so the idea was the z-statistic under the normal distribution 95% of the time came between plus and minus 2 STDs. This one, the t-statistic, 95% of the time, 99% of the time, will come between plus and minus some number of some t-scores that we'll be able to look up. So just as you use norm.inv to find the critical values of z, you can use t.inv in Excel to find the critical values of the t-score. So if we were interested in the margin of error, so 99% of all samples of size 36 fall not more than this number of STDs away from the mean. Well, there's 99% in the middle, 0.5% on each end. So the edge of the middle 95%, or the edge of the middle 99%, is at the 99.5 percentile. So you put in the 0.995, and then the other parameter here is this nu, it's n-1. So if your sample was size 36, the degrees of freedom, this nu parameter, would be 35. Okay. So, if we are doing this estimation problem, trying to estimate the population mean times per cell to divide, what we'll do is we'll get a simple random sample of 36 cells. We go out and we measure their division time, and so let's just make something up here. Let's suppose that what we get from our data was 31 minutes for the sample mean. Okay, and we find the sample standard deviation is 1.9 minutes. So the standard deviation of the sample mean is 1.9 over the square root of 36. So each standard deviation, 1 STD, is worth 0.317 minutes. And 99% of all the samples have a t-score between plus and minus 2.724 STDs. So the margin of error is 2.474 STDs times 0.317 minutes for each STD. And that's 0.863 minutes. So it's a similar list of things to memorize, like we had for the case when sigma was known. Here's the formula for your margin of error. The S is the sample standard deviation. The T star you can get from Excel. And the key step is just working out what area you need to plug in here in Excel. The way Excel is written, you plug in the area to the left of the point that you're looking for. So like if it was 95% confidence, then the area would be 0.975. If it was 90% confidence, the area would be 0.95. That's it.